Hello everyone. Uh, hello everyone. This week we will talk about energy sources and the technologies. The continents in this session are massive, but we will mostly focus on the fundamentals, the physics, the corrections. So you will be ready to walk through some of the basics in different energy technologies, including fossil technologies, solar, wind, hydro, and the nuclear. Most the clean and lower carbon technologies. Some sample analytical questions for this session. For example, how many solar wind capacities are needed to meet global energy need or energy demand? And how much land is required to meet such demand? For coal plants, how many coal can be, how much coal can be saved or emissions can be avoided if China, for example, or other country, the average coal power plant efficiency can be increased by 1% percentage point or 1%. This is a very interesting question, right? And you can do some simple calculations based on reasonable assumptions. Other questions like why combined heat and power saves energy. This is about efficiency in thermodynamics. How to design the layout of solar wind farms to improve production. Does wind and solar offer some can they be complementary to each other when they sit together? Those are some sample analytical questions that you can address using the tools knowledge that we will discuss in this session. The fundamentals is thermodynamics, especially for the fossil technologies we are talking about. Thermodynamics has an impact on efficiency, and that's key for the technology that has a huge impact. When we talk about energy numbers, when we talk about energy flow, as you recall, efficiency loss has a big impact on the energy consumption, right? On average, about 65% of the energy is lost during the conversion process. And any improvement on the efficiency will help us to address energy demand and emission challenges. Understanding the thermodynamic will also help us to compare different technologies. Which one is better? Which one has more power? And thermodynamics will help us address that. In physics, thermodynamics provides the physics limits, while in real world, its application will be impacted by many factors, such as technology, the pressure, the temperature, the material used, and the design of the system. Is there any combined cycle used in the system, etc.? Those factors will all impact the efficiency. But thermodynamics provides the physics limit. All different design of fossil technologies is basically a heat engine. As you can see here, it converts heat to mechanical energy or to do the work. And very often, the heat transfer from a high temperature source and do the work or convert to mechanical energy or kinetic energy, then the temperature coming down very often to ambient temperature. So no matter you're talking about a power plant, a jet engine, or your car engine, if it's a intercombustion engine, and it's fundamentally a heat engine, and you have heat source from high temperature and convert to the heat to mechanical energy, and then the temperature coming down to do the work. So this is a refreshment of a high school physics. There are laws of thermodynamics, right? The Zeroth law basically talk about if two systems are each in thermal equilibrium with a third, they are also in thermal equilibrium with each other. And the first law, in the process without transfer of matter, the change in internal energy is equivalent to the energy gained as heat, or the less of thermodynamics work, which means your work cannot exceed the energy you gain from the heat, because you always has an energy loss and conversion. And the second law, heat does not spontaneously flow from cold body to a hot body. It's always flow from hot body to cold body, unless you do work. So if no work is involved, heat is flow from hot body to cold body. And the third law, as the temperature of a system approaches absolute zero, all processes and the entropy of the system approaches a minimum value. If the temperature approaches absolute zero, then the entropy of the system approaches zero. So, those are the fundamentals. Will help out, and essentially, as I mentioned, is to help us to understand the efficiency. And the first law efficiency is the actual thermal efficiency, is the useful work as a share of the heat come into the system. So in this case, you can compare the heat source to the heat out of the system and compare to the heat into the system. And that's the actual energy used for to do useful work. There also a Carnot efficiency, which is the maximum possible efficiency of any heat engine or thermodynamic system. It has to do with the temperature. High temperature minus lower temperature divided by high temperature. That shows the maximum possible efficiency. So the lower temperature, as I mentioned, is very often the ambient temperature, which is 20 degrees C to under the range, right? From 0 degrees C to 40 degrees C, for example, ambient temperature. And the higher the temperature, the high temperature, the higher the maximum, the color efficiency. So that's why the design of the system is pushing the limit to high temperature, high pressure, so it can achieve high efficiency. You may see the term like supercritical, ultra supercritical. Those all push the pressure and the temperature of the high temperature as high as possible. And this will also help us understand why climate change has an impact to the system, which is the low temperature, right? So the higher the low temperature, the lower the color efficiency. So if climate change increase ambient or environmental temperature, then the thermodynamics efficiency of a thermal plant would coming down. So that has an impact on the power plant efficiency. That's from the fundamentals, physics, right? And the second law is comparing first law and color efficiencies, how much the system design can approach the maximum possible efficiency. The better the system, it can help us to achieve the maximum possible efficiency. Right? But in reality, the true efficiency, there will always energy losses, and it will impact the actual efficiency. This is a typical steam coal power plants, and from the flow, it will help us to understand how the power plant works. So there's coal pile here, right? At first, transit from through the belt and to the boiler or furnace. And combustion happens here, and the heat, it's the water converted to steam, and the steam drives the turbine, which generates electricity, and the electricity is transmitted through the transmission line to send it to the customer. And the steam convert to water cool down, and that circulates to the environment. Some power plants can claim this water to recycle the water, that saves energy and reduce the thermal pollution. And the pollutants and the carbon emissions are coming out from chimneys or the cooling stack, and the environmental technology are used to reduce the pollutants, reduce the particulate matters. So this is the design, and key process is to really get the combustion and improve the efficiency, and convert it to steam, which drives the electricity, the turbine to generate the electricity. So there are two fundamental cycles in designing the system. One is the Brayton cycle, and one is the Rankine cycle. The Brayton cycle is the jet engine and the gas turbine. It doesn't convert the there's no steam involved in the process. It's convert the fuel as compressed hot gas, and that gas drives the turbine and to do the work or generate electricity if it's a gas turbine. As you can see here, when you take the airplane, right? You take the the engine basically compress the air, and the fuel flows through the turbine and it drives the high pressure heated air drives the turbine, and which fly the airplane, right? There's no steam involved. So it's a jet engine, gas turbine, and the Brayton cycle, while in the Rankine cycle, it's a steam engine, a steam turbine. So the heat is convert the water to high pressure steam, and the steam drives the steam turbine to generate the electricity. So these two has to with different design. When we talk about jet or gas, especially natural gas power plant, very often it's the Brayton cycle. We are talking about the Brayton cycle. And if it's a coal plant, we first convert water to high pressure steam, which drives the generation, and that's a steam turbine. It's talking about the Rankine cycle. Both are named after famous physicists, which has contributed to the energy sector, and you can read more from the sources. So with those, it will make sense for you to recognize the key components of a typical real-world power plant. This Google satellite picture shows the largest coal plant in the US, the Georgia power plant, Shara. It has more than 3.7 gigawatt of nameplate capacity, and you can see if you can identify all the components in the power plant. For example, here is coal storage, where coal was transported by train and dumped here and prepared for use in the power plant. The generating units, as you can see here, and the cooling stack, which has the steam come out. Bottom ash landfill, after combustion coal has ashes, right? It through the belt, it was transit to the ash landfill. Substation, as you can see here, the electricity has transit and raised the voltage in the substation and transited through the transmission lines. Waste pollution management, the landfill, the ash is a kind of waste, and also the air pollutants and other regulations partially is here. So with this, you can from any power plant, you can quickly identify the components, and I posted here there actually a project to use Google satellite data to identify the generation of a specific power plant to monitor its pollution. This is a new technology to help you to do research and do some monitoring work. It's a great tool to really help make decisions. Combined cycle, which combine the Brayton and Rankine cycle, or the gas turbine and the steam turbine, and that will help improve the efficiency. So you can play the video which explain this concept very well and at your own pace. The basic idea is use the gas turbine first. So they are exhaust heat, and using that heat to drive the steam turbine. And with this combined cycle, it can improve the efficiency from 40% to 70%, even higher. This improve the system efficiency, and if we plus the exhaust heat from the steam turbine, and for district heating, the efficiency can be even higher. Through those measures, it will improve the efficiency of the system. So that's the fossil plants, and most important concepts is the efficiency, how to using the combined cycle different design to what are the factors who contribute to the efficiency. Now we can move to one other technology or renewables is wind. To understand the wind, fundamentally, wind is the kinetic energy embedded in a moving air mass blow. That's the wind, right? So what's the energy in the wind? It's the kinetic energy of the moving air mass that drives the turbine. And the energy in the moving air mass, or kinetic energy, is the half mass multiplied by velocity or wind speed to the square. And because we are talking about the power, right? So the distance of a air move is v multiplied by t, and that's the energy divided by t, and t canceled. So we got m velocity to the cubic, as you can see here. And the sweeping area, that's the area of the turbine, and we know it's pi rotor. That's the larger of the rotor to the square. And as you can see here, so the larger the turbine rotor of the turbine, the larger of the power, and that relationship is a square relationship. And the larger the velocity of wind speed, the larger the power from wind, and the relationship is to the cubic. And this is exponential relationship, as you can see here. And you can, through this formula, you can calculate how the rotor, the rotor, how long the turbine, how big is the turbine, how that contribute to the power you can harvest with the wind technology. Rho here is the air density. So that's a very often a given number, and it changes varies over different elevation, different location, but it's comparatively constant. So this is the fundamental physics. It's the kinetic energy embedded in moving air mass. And there are, as we see in the color efficiency, in wind turbine design, there's a Bend's law, which is the maximum possible efficiency of any wind turbine can achieve, which is about 60%, I think 59.3%, because wind cannot stop right after moving through the turbine, right? If it stops, then there's no constant air mass can moving through. So it has to moving through, but wind speed will coming down. And the ratio between upwind speed and downwind speed and upwind speed described the relationship, and the optimum of this is 1 to the third, which means that when down speed is 1/3 of upwind speed, the system provides the maximum power, and that's Bend's law, 59.3%, the maximum wind power it can achieve. So the formula we discussed before described the instant power, but very often we were given the average wind speed of a place, for example, Stony Brook or any other place. How do we get the power from an average wind? This we will need to understand the distribution of the wind, and that's called Rayleigh's distribution, or it's a special type of Weber distribution that describes the distribution of wind speed over a year, for example, because we have some hours has higher wind speed, some hours have lower wind speed. If we plot the wind speed distribution of the wind speed, it's close to the Rayleigh's distribution. And to calculate it, the relationship is which is the area, right? So the average power is about 6 divided by pi. If we use average wind speed in the instant power, that means if we use average wind speed, we have to multiply by 1.91 to get the average power. That's a very important concept, because very often we only have the average wind speed. And in this case, in order to get the average power of, we need to multiply by 6 divided by pi, which is 1.91. And that will help us do a reasonable estimation. So if you use instant power, for example, to do the calculation, also if you use average power in the instant power formula and forgot to multiply 1.91, then you got less power you would have in your power plant. This is a very important correction that you need to aware. So how a turbine responds to the wind speed, that is the so-called power curve. as you can see here, it's very close to a logistic curve, and there's a cut-in speed. That's the minimum wind speed that can really move the turbine. The turbine has some cut-in speed, right? That cut-in speed is minimum speed. Otherwise, the turbine wouldn't move. Wind is too small to drive the turbine. And then there is a maximum power that's designed by beyond that end. Because of the mechanics, even you have higher wind speed, the power reaches its maximum rated power, it won't continue has higher power. And then there is a cut out speed. That's the maximum speed, wind speed that this wind turbine can bear. Beyond that, it will broken the turbine, so it will basically lock the turbine from spinning to protect the turbine. Otherwise, it's spinning too fast and it will destroy the turbine. So that's a cut out speed. As you can see here, it's about 20 to 25 meters per second. And the dots shows, so first, this is research from NREL, National Renewable Energy Laboratory. The red dots show, square dots shows the theoretical power curve of this type of a turbine. And those dots shows, because there are many such turbines in the power plant, in the wind farm, and each dot shows the actual cut-in speed and actual cut-out speed, and it shows the distribution. But those shows the theoretical power curve, and in the real world it might diverge from the theoretical, but this gives you a sense. And very important to understand cut-in speed, cut-out speed, maximum power, and the shape of the power. You would need the power curve of different type of a turbine, and to get the actual power output, to simulate the power output of this type of turbine. So as you can see here, when wind speed reach more than 10, 12 meters per second, it reaches maximum power. You cannot keep going as the cubic relationship. So in the simulation, very important to use the power curve of a specific wind turbine, and those you can get the system advisory model, the same model I mentioned in homework too. There are some very important corrections. For example, as temperature change, rho, the air density would change, and you can see here, and attitude, it will also change. The power, at the higher the attitude, the lower the air density. Tower height also has an impact. So you would need to know the factors to use to do the correction. For example, here you would need to know the friction coefficient that has to do with the surface condition. For example, forest would very often slow down the wind, while in desert or in surface, in water surface, the friction coefficient usually lower than those in the rough surface. Solar it's another very important renewables we are talking about in the IEA's net zero scenarios by 2050. Solar wind will play the most important roles to deliver the renewable energy or clean energy we needed. Solar fundamental physics is lights, and it has to do the fundamental structure or design to make solar work is the so-called PN junction, and this really has to do with some of the fundamentals in the atomic physics, why silicon is used in the PV module, for example, because it has, we've combined with different material, for example, phosphorus or barium, it can create the P-type or N-type of silicon that has a free electron or free hole that can attract the electron. Once there's some hit the P-type, which has a one free electron, the electron in the sun, which, or the photon in the sun activate the electron in the P-type, and that makes the electron active, and that can flow through the electric and field the hole in the barium P-type silicon. So that flow creates the workable circuit, power circuits, and that's exactly how the design work. And improvements of the system can be using anti-reflection coating to reduce the reflection and reduce the temperature, so the system can work better to improve the P-type or B-type of design, so to make the system run more efficiently. There are other materials, that's those are all hot research areas for any, but mainstream technologies relies on silicon for the design. Here is another video that maybe explain those concepts better than I do. So please just take a quick review of those at your spare time to learn how to work. We will talk about important fractions. So the power or the energy for the solar system fundamentally is coming from the sun, right? So the position of the sun has impact on how much energy power we can get from the solar system. So in order to do that, we need to know the solar position at any time of the day if we want to know the instant power we can get from the system. So that we have altitude angle, latitude angle, zoom angle, hour angle, and how we can use those angle to do the calculation, do the correction. Radiation also has the direct beam radiation, diffuse radiation, and reflected. Direct is how the panel received from the direct radiation. Diffusion radiation is when the radiation hit clouds and aerosols it diffuse, and those though there are some come to the solar panel, and they are also reflected. That in the end is the total radiation that the panel receives. The tracking also improve the radiation we receive from the solar. They are fixed, like fixed rooftop. It's no matter which season, it's fixed on the roof, right? But in the commercial utility scale solar projects, very often it has track system, has one axis or two axis tracking. It can move in directions or up and down, so it always face the sun vertically to receive the best direct beam radiation. So those are corrections that will help us to calculate instant power for solar system and to improve the efficiency of the system. And Gil Master's book posted those chapters on bright space. It's probably the best source you can see to how to explain how those concepts work. Please review those chapters and at least to get an idea of what those corrections are and how to do the corrections. You don't need to remember the formula. You can always find it, but it's very important you know those concepts. So I'll go very quickly on the two other technologies, which is fundamental physics, and one is hydro. Hydro is basically the gravitational the energy in the gravity of the water, right? So you created a reservoir using dam, and that has high potential energy, and using that potential energy drives the generator turbine to generate electricity. And the energy in the has to do with the height, how high is the dam, and that's what we can see here. And another related is the pumped storage. Hydropower is still hydro, but it serves as storage. This is increasingly important as we bring more renewable solar and wind, which are variable, and pumped storage hydropower provide cheap, reliable storage that can help integrate those variable resources. So the idea when we have excessive wind and solar or other energy sources, we pump the water to a higher elevation reservoir. And when we need the power, we run the storage, pump storage hydropower as a conventional hydropower, and to provide the electricity we need. So both hydropower and pumped storage hydropower has requirement or restrictions on where they can build, and it has other impacts such as ecosystem impacts, culture and historic impact, because the reservoir can flood historic cities, towns, villages, and it will flood forests and create some geologic incidents or accidents. Those are, and people has to be relocated if in the flooded zone. So there are different. The dam also created ecosystem impact for fishes and other ecologic impacts that rely on the river for their survival. So it's debating, it's controversial, but it's important renewable energy sources. Nuclear, I will not talk too much detail, but only the fundamentals. We have nuclear fission and nuclear fusion. For fission, is really the neutron that hit uranium and break uranium to two different lighter elements, and there are huge energy in the bonded when the bonded energy that break the boundary, and that created the uranium energy that we harvest. And the chain function can be very fast. That's why the atomic bomb is so powerful. So nuclear power plants is basically using different technologies, no matter what generation of the technology you're talking about, to try to control the process so we can harvest the energy in a peaceful way and reliable, safe way. And for the costs related to nuclear, as we discussed in the learning curve case, it's going up, right? Partly because we have regulations to address the safety. There's no, it's always put the safety first, and not risking it. And also because the treatment of the nuclear waste to avoid the proliferation or potential human health impact of the nuclear waste. Those two factors drive the cost of nuclear high. Fusion is also fundamental physics that two lighter elements combine to a higher energy elements, which release energy in the fusion. Fundamental physics, we understand it. In the reality, how to make it work at the initial stage, it needs high energy to make this happen. And this is still an area to research for commercial use of a fusion. Maybe in the future, or not too long future, we can make commercial fusion work, and it will help fundamentally address our energy generation. So this is a really frontier for research, and it's still in research. So nuclear technologies, regulations, those are for you to read in your spare time if you are interested. I will just summarize what we have discussed in this session. The series of the energy technologies or energy sources has to do with the excuse me. Fundamentals of physics. Thermodynamics will help us to understand fossil technologies, gas plants, oil plants, coal plants. Wind is kinetic energy, so kinematics will help us to understand wind. solar, it's light, and semiconductor will help us. So how solar work, gravity will help us to understand hydro and tidal energy, and atomic physics will help us understand nuclear. So try to link the technology with the fundamental physics we are talking about, and with the understanding of those physics really help us to understand the different technology sources and how they work. In real world, we need to get familiar with all kinds of corrections based on real world situation. For example, longitude and latitude, friction coefficients based on the surface area, elevation, which has an impact in air density, which impact the temperature and other factors which will impact how much power we can get from wind and so on. The physics are fundamental; they don't change. They are there, but the corrections will help us to do better job in simulation and projections, and that's very important when we try to get the simulations right. So that's what we have discussed in the energy technologies and sources. Please read GeoMaster's chapters. Those are great resources for you to really dive into the specifics. That's all. Thank you.